All right, so this is just a quick little overview as to what you are supposed to like extract or infer from last week's activity on desmos. Um, we are in the last chapter of pre-calculus. It's very much is like the first chapter in calculus. Calculus is the study of change, of rates of change. It's also study of the infinite. Infinite you often think of as big, but infinite can be very small to infinitely small. And we talked about this whole like difference quotient thing, which was really evaluating the slope as h approaches zero. So we're looking to move from average rate of change to instantaneous rate of change. And a lot of this activity has to do with what does that actually look like? Well, that's the slope of a curve at any point. Um, and there were these screens where it was showing you like this screen is just to show you that the slope is changing, and I could trace the slope of this curve like as if it was a ruler tangent to the curve at any point, and it would change. And I think what is also true is that I could shift this curve up or down, and those tangent lines wouldn't change. If I just shifted the curve up, then these slopes would be the same. And that's an important concept, but I don't think it's one that was very evident for everybody that was doing this. But you could, you can look at the curves, the way that the curves are changing, or the way the tangent line is changing, and and graph the curve. This screen I thought was particularly difficult to understand what it was saying. But notice what's changing in all these things is just the constant. And in the linear, it's the same. The only thing that's changing is the constant. It's a constant slope of 2. In the quadratic, the slope isn't constant because in a nonlinear curve, slopes do change. But you find that in polynomials, they actually change at a constant rate. It's a little bit of a high-level concept, but in all of these things, what's changing is simply the constant value at the end, the d value. And remember, especially with trigonometric graphs, we talked about what does that d affect? It affects the midline, which is the middle of the graph. And the point here is to show you that adding a constant does not change the curvature of the graph. It just changes the position vertically. And that's related to slope that we'll get into a little bit. What I think you should know, what I wanted to show you about slope, is that there's a relationship between the graph and its derivative. Okay, so derivative is a calculus word where it's legal for us to use it now because we're in the last chapter of pre-calculus. Derivative is difference quotient, the limit of f of x. Let's see. The limit as h approaches 0 of f of x plus h minus f of x divided by h is the derivative. It's the instantaneous rate of change, and it's also what we call f prime of x. And if I think of what does that mean? Well, if I look at this function, I'm going to divide it up into 3 different parts. This is part number 1, this is part number 2, and this is part number 3. And what is happening in those different parts? Well, if I look at part number 1, what is the slope? The slope is positive, right? So what should I see about the derivative? Well, the derivative should be positive, okay? And let's see if I can divide the derivative up into the same parts too. This is part 1, this is part 2, this is part 3. And notice that the slope here, slope equals positive, and then this is above the x-axis. Okay, so this is the value. If I go over to the value, it's a positive number. It's decreasing, the function is decreasing because the slope here starts steep and it's getting flatter. And then at some point, the slope is 0, okay? Where the function changes directions, the tangent line is horizontal, meaning the slope is 0. That's important because what you see in the derivative at the point where you have a horizontal tangent in the original function is a 0. Okay, so that 0 is kind of important. And then what happens in region 2? Well, the slope of the tangent line in the original function gets steeper, and then at some point it gets flatter, but the whole time its slope is negative. I'm going to put that NEG there. So the slope is negative, and what do you see in this? Well, these things are all below the x-axis, so it's negative, and that makes sense. And then at some point, the slope is 0, and the slope goes from negative to positive. What happens when that slope is 0? Well, the same thing. That's on the derivative where you see the function crossing the x-axis. So this, at this point right here, m is equal to 0, and on the derivative right here, you have a 0. What's happening in the third section, the slope is positive, the tangent lines are positive, and the slope here is positive. Another thing you might notice is that this looks like a cubic function, and this looks like a quadratic function. And that is not a coincidence. That's what happens when you go down the derivative line. Your power goes down by 1. I'll show you how that works analytically in just a second. But those are the takeaways of the derivative. These are all things that get re-emphasized in calculus. And so if these pieces are still falling into the place, that's normal. But you can do yourself an advantage by starting to think like this. If you look at the original function and the slope function or the first derivative, you can make this connection. Here is 0 and here is 0. Okay? Here is 0 and here is 0. Here is a positive slope, and that is the same. Like if I'm saying this right here is a positive slope, that should be consistent with the highlighted part in the derivative where the slope is above the x-axis. This function just keeps changing. This is a sine, or what is this one? Yeah, this one's sine of x. And notice that there is no, like in a polynomial function, you have the tails that go to infinity or negative infinity. There's a certain number of humps. And then in the derivative function, there's going to be one less turning point. But in a function that has an infinitely many humps, like in a trigonometric function, the derivative is also going to have infinitely many humps. And that brings me to the last thing, which is the power rule, which some people, their tutors will teach them this at some point in the year anyways, that there's a simple way. You remember when we did this whole difference quotient limit as h approaches 0 of f of x plus h minus f of x? This is one of the greatest joys of a teacher is when we show you that all this work that we had you do was for naught, because there's a much easier way for you to solve these things. If I say, let's do it with a second degree thing. So y is equal to 1/5 x squared. I'm going to say y prime is equal to 2 times 1/5 times x to the first power. So the power goes down, and then you subtract 1. So this is 2/5 x. If I say y is equal to, actually, let's just write it in here. Y prime is equal to 3x squared minus 4x minus 4. Okay, notice that this, you could think of this as like 2x to the 0, and the 0 comes down and you get 0, or you could just remember that when you have a constant and you take the derivative, that number goes away. This one, well, you don't need to know this, but this is 3 cosine of x. The derivative of sine is cosine. But this idea of the derivative being the same as the difference quotient function that we learned It's the instantaneous rate of change. It's the slope of the tangent line. It's the, I guess, microscopic rate of change when you get the limit of the span you're measuring goes down to zero. Um, that's an important topic. That's an important takeaway out of chapter 13. And those desmos activities that we were doing were bridging the gap from what we've learned so far to where this stuff is going in calculus.